All right, let's dive into what is honestly one of the biggest, most nagging puzzles in all of fundamental physics. We're talking about a question that doesn't just poke a hole in our theories, it threatens our whole picture of why the universe is so stable.
So, have you ever stopped to wonder what's actually protecting our universe from just collapsing? I mean, all the forces, all the particles, why does it all hang together so perfectly? Well, the answer we have right now, it's kind of terrifying. It points to this cosmic balancing act that seems completely impossible.
Yeah, it turns out our stable universe seems to rely on an unbelievable coincidence. Seriously, imagine trying to balance a pencil perfectly on its sharpest point. Now imagine that pencil has been balancing there, not for a few seconds, but for the entire age of the universe. That's the level of precision we're talking about. It's so absurdly unlikely that physicists are basically saying, no way, this can't be an accident. Something else has to be going on. Okay, so to really get why this is such a big deal, we've got to look at our best rule book for the universe. It's called the Standard Model of Particle Physics. And look, this thing is a masterpiece. It's one of the most successful theories in the history of science, predicting everything with stunning accuracy. But it has this one glaring, massive flaw. So here's the deal. For almost every other particle out there, its mass is protected by these deep, fundamental rules of physics we call symmetries. You can think of them like cosmic bodyguards, making sure the particle's mass stays stable and sensible. But then there's the Higgs boson, the all-important particle that gives everything else mass. Well, it's the odd one out. It has no bodyguard. Its mass is just out there, totally exposed to all the crazy high-energy stuff happening in the universe. And this is where the problem goes from a little weird to absolutely colossal. Because the Higgs is so vulnerable, it gets caught between two wildly different energy scales that run the universe. And the chasm between these two scales, that's the heart of the whole mystery. So, on one side, you've got the energy scale we can actually test in our labs, like the Large Hadron Collider. This is where we found the Higgs, and it has a mass of about 125 giga-electron volts, or GeV for short. This is called the electroweak scale. It's kind of like our home turf in physics. But then you look at the other end of the spectrum, and there you find something called the Planck scale. This is the energy where gravity is supposed to become just as strong as all the other forces. We're talking about an energy level so high, it's almost impossible to wrap your head around it. It's basically the edge of the map for physics, as we know it. And when you put these two scales side by side, the difference is just staggering. The Planck scale is roughly 10 to the 17th power bigger than the Higgs mass. That's a 1 with 17 zeros after it. We're talking about a 17 order of magnitude gap. That's not a gap, that's a cosmic canyon. Look, to really visualize this, if that huge bar represents the Planck scale, the bar for the Higgs mass would be, well, you literally couldn't see it. It's smaller than a pixel on your screen. It's like comparing the size of one single bacterium to the size of our entire planet. It's an insane disparity. All right, I know what you're thinking. So what? Big numbers, big deal. Why is this huge gap a problem? Why is it a full-blown crisis in physics? Well, it all comes down to the fundamental rules of quantum mechanics. See, according to quantum mechanics, these two scales shouldn't just be sitting there minding their own business. The insane energy of the Planck scale should be yanking on the Higgs, pulling it around, and the result should be, well, catastrophic for our theories. Remember how the Higgs has no bodyguard? Because it's unprotected, quantum theory says that all this high-energy stuff from the Planck scale, this whole sea of virtual particles popping in and out of existence, should be constantly tugging on it. These are called quantum corrections, and these corrections should be so powerful that they drag the Higgs mass all the way up to that ginormous Planck scale number. But they don't. For some reason, the Higgs stays tiny. So here's the calculation that's breaking physics. You start with what we call the Higgs's bare mass. Then, you add in those huge quantum corrections that our theories say must be there. The answer you expect to get is a massive number, right up near the Planck scale. But the number we actually measure in experiments is a measly 125 GeV. So how is that possible? The only way the math works is if the bare mass is an equally massive negative number that cancels out the positive corrections with almost perfect, miraculous precision. And when I say precise, I mean impossibly precise. We're talking about a cancellation that has to be accurate to 1 part in 10 to the power of 34. That's a 1 with 34 zeros. It's so ridiculous, it's like throwing a dart from Earth and hitting a specific atom on Pluto. Physicists call this fine-tuning, and it's a giant red flag that our theory is missing something huge. This whole mess flies in the face of a guiding idea in physics called naturalness. It's basically the principle that the universe shouldn't rely on insane coincidences. The numbers in our theory should make sense. They should be natural, not the result of some cosmic miracle. And the Higgs mass is about as unnatural as it gets, which tells us the standard model just isn't the final story. But here's the cool part. This crisis isn't a dead end. It's the opposite. It's the #1 motivator driving the search for new physics. It's the biggest clue we have that there's a deeper, better theory out there, and scientists all over the world are on the hunt for it. And this hunt has a game plan. At places like the Large Hadron Collider, physicists are smashing particles together to see if they can create new ones that aren't in the standard model. They're exploring some really wild ideas, like supersymmetric partners, or a Higgs boson that's actually made of smaller particles, or even extra dimensions of space. It's all about trying to find a natural explanation for this mess. Let's look at two of the leading suspects. First, there's supersymmetry, or SUSY for short. The idea here is that every particle we know has a hidden superpartner particle, and it just so happens that the quantum effects from these new partners would naturally cancel out the bad stuff, protecting the Higgs. It's an elegant solution. Then you have theories about large extra dimensions. This one suggests that gravity isn't actually weak. It just looks that way because it's leaking out into other dimensions we can't see. If that's true, the real Planck scale is much lower, and the whole giant gap problem just vanishes. So we don't have the final answer yet. But the key takeaway here is that the hierarchy problem isn't a failure. Far from it. It's our most important clue, our clearest signpost, pointing us toward what's next, a more complete, more fundamental understanding of reality. And believe me, the stakes are as high as they get. Solving this mystery isn't just about tweaking one little number for the Higgs boson. It's about bridging that 17 order of magnitude gap. It's the key to finally uniting the two great pillars of physics, quantum mechanics and gravity. This is the path to a true theory of everything. It's like one physicist said, finding the solution here isn't just about patching up a hole in our math. It's going to redefine our entire understanding of the universe's architecture. It'll change everything. So the next time you look around at our universe, which seems so stable and predictable, just remember this insane, unnatural coincidence that's sitting right at its very foundation. It's the biggest mystery out there, and it leaves us with this one huge, tantalizing question. What hidden law of nature are we missing? What's really holding everything together?